Hello everyone, and welcome back to a new episode of Advent of Code. As I mentioned in the last episode, we're working through the backlog of puzzles that I've finished but not yet narrated, and we are on to day 15 now. Dueling generators. Here, you encounter a pair of dueling generators. The generators, called Generator A and Generator B, are trying to agree on a sequence of numbers. However, one of them is malfunctioning, and so the sequences don't always match. As they do this, a judge waits for each of them to generate its next value, compares the lowest 16 bytes of both values, and keeps track of the number of times those parts of the values match. The generators both work on the same principle. To create its next value, a generator will take the previous value it produced, multiply it by a factor, and they give some numbers that A and B use, which are not part of our input, but just fixed constants, and then keep the remainder of dividing that resulting product by this large number, which looks an awful lot like 2 to the 32, but isn't because it's odd. I think it's 2 to the 32 minus 1, but I'm not sure. I didn't bother to check. That final remainder is the value it produces next. So we're multiplying by largish numbers and then modulo a largish number. Great. To calculate each generator's first value, it instead uses a specific starting value as if it were its previous input, and so that previous value. And so that's our actual puzzle input, is what are the previous values for A and B, not what are their multiplicative factors. I got that mixed up a number of times. So for example, they're like, okay, here you go. Here's some examples. They produce some binary bits, and like, oh, look at this. Here's the one where the bottom 16 match up. So we're just being asked how many times in the first 40 million numbers do the bottom however many match up. And our puzzle input is actually worth looking at briefly. I don't know. It's pretty boring, I guess. Pretty simple to match with the regex, but honestly, I don't know how to use regexes in Haskell, and Haskell's so great that you don't need them, so there. All right, let's start looking at the puzzle solution. And just like in some previous puzzles, I committed here a version, my first implementation, which I thought should work. Honestly, I have not looked at this puzzle for 2 weeks, and I don't remember what it was that I thought would work. But apparently I had some version that I thought would work if only I had infinite memory, but in fact we don't, so I had to find a better version. So let's check out this first version and see what I was up to. What did I do? Okay, fine. Well, I have a learning something to say that is related to some code that I didn't write but that I should have written, and I'm not sure when is the right time to talk about it. Let's actually leave it alone for a minute and just talk about what's written here. I defined, so my idea for this, that's why I thought that this would work with infinite memory. I remember now. My idea was, well, we could sort of have a, this would have been way easier if I had just modeled things slightly differently, I'm now realizing. Anyway, I said, oh, well, we have a bunch of generators, right? Why doesn't this work? Anyway, and I thought rather than like having an iterative process that remembers what the generator seed was and what the current value is and computes the next one from the previous one as part of my solution to part one, what if I instead, the moment that I parse a value, I parse the generator for A and say here's how much it should multiply by every time. Or what its starting value was, of course. What it should multiply by every time is fixed. What if I just produce a list of all the values that it ever will produce in the universe and make an infinite list of that, right? And do that similarly for B. And then I now see why, anyway. And then we'll have the answer, right? we do some filtering on that list of states, and our main like sort of bookkeeping, our business logic of a sort for deciding whether two numbers are good doesn't have to know anything about how to generate more numbers. So we have our program neatly divided into two parts, one that generates numbers and one that checks numbers. And I think this is quite nice and clean, but it doesn't work for a reason which is somewhat subtle. And we'll talk about what that is once I've explained this implementation, I guess. So I have basically, I call parse, which is a really simple function. Where even is parse? Here it is. It's so simple I couldn't even see. We just, given a line, we call words to get the words of the line, we call last to get the last word, and then we call read to get an integer out of it. And read, of course, knows that we're reading a string, and since the result of the function is expected to be an integer, the compiler knows, okay, I'll read the string as an integer. The magic of static types and amazing type inference. Anyway, so what we do then, we've parsed it, and we call this vals function, which is really simple. We just iterate next. And I've written here, because iterate composed with next is a really... This is another example of a time when I think it is not... the point-free solution is not best. It's simpler to write one of these two things, but this is the most dense, and it's always fun to spot chances to write this. The simple thing to do would say, well, vals takes a factor and an initial value, and iterates by calling the next function produced from that factor on the init value. And next is just multiply them together and take them mod whatever. And so, fine, you could write that. But look, we have this init function at the end, which is just being passed along. You could Ada reduce that and omit it and let currying take care of it for you. And so you could say, vals of factor is iterate next of factor, right? Seems good. But then you look at this and you say, wait a minute, I've just written f of x equals g of h of x. Well, what does that look like? That looks like function composition, right? Yeah, it does, and you can totally write that. Compose together the functions iterated next. I don't know about you guys, but I find it hard to think about what it means to compose a 2-argument function with a 1-argument function. And it all works, but like only because Haskell treats all functions as if they were of 1 argument. And so you kind of like, you call next with 1 argument, and then you call iterate with the result of that, and then you call the result of calling iterate with the second function. And so like, I don't know, second value. It's not very clear what's going on here, but I thought it was cool to spot, and so I wrote it. But really, one of these other versions would be more understandable. And so next is, of course, very simple. We talked about it. And part 1 is a composition of a number of functions, only one of which is interesting at all. We obtain somehow a list of booleans, and we count them. And that's the answer, right? How many times did it match? We take 40 million, because that's how many things the puzzle says to look at. And this is the interesting function, right? What the heck is going on in here? We'll put it on a new line so we can examine it more carefully. The uncurry. Right. So uncurry is what we'll talk about first. Haskell functions are all curried, which means if they take, say, 2 arguments, then really it's a function taking 1 argument and returning a function of another argument, which when called calls the original thing with both, right? Like, okay. And usually that's a more convenient way to work with functions in Haskell. However, on occasion, it can be useful to deal with what you might call the uncurried version of a function, something that doesn't want 2 arguments at all, but just wants a single one, which is a tuple. And so uncurry does that for you. Uncurry f and xy equals fxy. So all it does is it wraps a function up that would expect 2 arguments and makes it expect a tuple of 2 values instead. By saying, call uncurry with a function and a tuple, and I'll call that function with the 2 values in that tuple. Okay, so we're calling uncurry because states is a list of tuples. And we want to call this zipwith function with the 2 values in those tuples, not with the tuple itself. We basically zip together the list of states with this function by using uncurry on the way. And that function says, basically, it uses on, which is this amazing function. I love on. On basically is written, let's see, f on xy equals, wait, f on g of x and y equals f of gx gy. Yes, that's correct. Okay. The idea is you often say, oh gosh, I want to see whether the first object in these 2 different lists are both the same. And it's kind of annoying to have to call first twice on those 2 lists and then call this equals on the result or whatever. And so, you know, and you can also like write sort of interesting stuff. You can say comparing on first, for example, is like sort by comparing on first of x's or whatever. Is a thing you can write by using this cool on function. But it doesn't have to be comparing. You can use it for any binary operator that takes 2 values of the same type. If you have 2 things of a different type that you know how to convert to that first type. So this function here, equals on mod 65536, is basically a function which takes 2 values and checks whether their lower 16 bits are the same. Pretty cool, right? Like, how would you... This function is so amazingly terse. Like, how would you write that in some other language? Let's say C, right? C doesn't even have lambdas. Oh my gosh. Let's write in a language with lambdas, right? Python. Well... Python sort of has lambdas. But in order to call zipwith with our lambda, it would be... it's fine. It would be a single... we could do it as a single line lambda. If Python probably has zipwith, and if it doesn't, you could write it. You could write zipwith lambda x, y, x equals y of... like, what... I guess we're writing this lambda, right? Lambda x, y, x... Does Python... Oh, Python's mod operator is this, right? X mod 655... I keep forgetting I don't have the numpad one. Like, I haven't figured out how to transmit the numpad across my SSH tunnel in PuTTY. And, like, I don't know. I'm sure I could do it, but... Anyway, every so often I try to type a number with the numpad and it, like, doesn't work. Oh, we need to put commas in here. Python loves commas. I always forget commas when I'm switching to a language with commas. So it would actually look sort of like this. Anyway, the point is, like, on lets us write this snippet without even needing a lambda. So the verbosity of the lambda in our language doesn't even matter. It's really nice, I think. Anyway, so zipwith the 2 states from our infinite list of states, whether they are equal on their lower 2 bytes. And then we do all the stuff we talked about before of length and filter and take and so on. Okay, so great. I explained all this and it seems like it should work. Why does it not work? The answer is actually, in a way, that it totally does work. This part1 function is lazy. It takes an infinite stream of inputs in, processes them one at a time, and produces an integer as its output. That's fine and lovely, and it works. However, it doesn't work because we've got part 2 in here. If I actually were doing just part 1, this would be fine. But this is something you get used to when working with lazy languages like Clojure or Haskell or whatever. is you're used to processing infinite lists just like fine. You know, it's totally routine. When you're working with such a language, you just process it from start to end, and the garbage collector takes care of it as you go. But if you can't throw away the intermediate results as you process them because you need to use them again, then you end up having to hold that whole gigantic sequence in memory. And so we would need to hold 40 million values in memory at once, which is not impossible, but the default amount of memory allocated to Haskell on this particular computer, it doesn't hold it. Maybe I could add more memory, but really I just shouldn't do this dumb thing, right? It's not a humongous improvement to treat this as an infinite list of states, I think. Maybe I could have left part 1 alone and then figured out what to do with part 2 later, but I don't know. It doesn't seem practical because we can't possibly deal with this infinite list twice. So all that happened, and hello, why did that not? Oh right. I guess I just want to check out. Okay. And now let's check out. Check out this working function. And basically what I did was, instead of creating the initial values forever, I just passed in the list that we were supposed to use. Not the list, the initial value. And now part 1 is a lot more complicated, basically, right? It has to say, it can't be like, we can't just use this uncurry zip with thing anymore. We have to take A and B and deal with them explicitly. We call this whole function on the result of calling zip with our zipping thing, but now we have to pass zip with its arguments explicitly. Iterate next of this value A, iterate next of this value B. It's all quite a bit clunkier. And it leads me to the thing that I said at the beginning that I had written wrong and should have done better. Which is actually something I should have mentioned a minute ago. We're dealing both with ints and integers here, and I don't remember if I've told you guys about the distinction. Int is Haskell's sort of default limited integer type. It's around 32 bits, or maybe 64 bits. No guarantees, but it's guaranteed to be at least like 28 bits or something, 29, I don't know. And so when we care about working with large numbers, that's not really ideal. And we could use something that's guaranteed to be exactly 64 bits because these numbers certainly do fit in 64 bits. But it's often in Haskell simpler to just use integer, which is the built-in arbitrary precision integral type that will handle integers of any size at all using, I guess, some high-performance big int library. Probably GMP or whatever. Anyway, so that's why we have ints and integers. But, which brings me to the function next. It takes 2 integers and returns an integer. And that's all very nice. And in fact, as far as next is concerned, it doesn't even matter which integer is which. Pass them in any order at all. Which is why I thought it was okay to just leave them as integers. But while doing part 1 and part 2, I consistently struggled with mixing up which argument was the seed and which one was the factor. Because I constantly kept thinking that the factor is the obvious thing you would vary, and the initial value would be the constant. And so I kept mixing up which thing I read from my input, and which goes to which value. And it doesn't matter as far as next is concerned, but it does matter as far as like part 1 is concerned, because it partially applies next with one value and calls iterate with the other value. And by making the types of these things just be integer, I'm not letting the Haskell compiler help me out at all. So it would have been better to at least define a type alias for these two things give them better names, one of them be factor, like call one of them a factor and one of them be a seed. That would mean we wouldn't have to change the calling code at all, though. And the calling code is what I kept making mistakes on, since of course next doesn't care. So I think that it would have been, in retrospect, it would have saved me a great deal of headache to actually define a new type wrapper. Say new type factor A equals factor. Well, actually, just say new type. We'll just make it a wrapper out int. It doesn't need to be parametric. Factor of integer. And then, if we change next to take factor here, it would become illegal to call next with an integer that is not wrapped up in this factor type. And we would have to say, in fact, factor f. We would have to destructure it every time here. And perhaps, you know, we could do the same thing here and make it be init or something, or seed, to find another new type. And in that way, assuming that I constructed my values, well, I would now be forced to construct my values giving them explicit labels as to how I plan to use them in the future. Which will make it much, much harder for me to make the mistake that I made over and over of mixing them up. And this is something like Haskell has a very strong type system, and it can help a lot with the built-in types, and that's great. And of course that gets you a long way. But it's more than that. You can ask for more discipline, right? You can say, look, here's a new type. Often, of course, new types are used for some other reason, but this is one of the reasons they can be used. You know, people often give Haskell as an example of, like, you know, that famous example of when some space shuttle or spacecraft of some sort mixed up meters and feet or whatever and blew up. Well, you know, if they'd used strong types and labeled them as a metric value, and it would be impossible to accidentally use it as an imperial value, for example. And I don't always see ahead of time the kinds of mistakes I'm going to make, and so I don't realize I should tell the type system to help me out. That's something I'd like to get better at, but it's something that you can do in Haskell quite simply. You can just say, here's a new label for my type, which I demand that I always wrap and unwrap whenever I want to access what the real value underlying it is. And this is a zero-cost abstraction. It doesn't... At runtime, it's just an integer. But at compile time, you have to do this little dance of constructing it and destructing it to get at it in order to tell the compiler, yes, 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 I really know this is a factor. I really want to treat this as a factor and not as a seed, or whatever. So I think that would be an improvement. Certainly would have made me solve this puzzle much faster had I written that. I'm not going to commit it right now because we're in the middle of time travel. Right? Like we're looking at a past version where I just solved part 1. So anyway, part 1, I just take the seeds in instead of the whole value sequence, and I construct the infinite list inside of the scope of part 1, which means that it can be thrown away as it's progressed, and we can move on to part 2. Okay, so, no spoilers. Let's look at part 2. In the interest of trying to align a little better, the generators get more picky about the numbers they actually give to the judge. They still generate values in the same way, but now they only hand a value to the judge when it meets their criteria. Generator A looks for values that are multiples of 4, and generator B looks for values that are multiples of 8. Each generator functions completely independently. They both go through values entirely on their own, only occasionally handing an acceptable value to the judge, and otherwise working through the same sequence of values as before until they find one. And the judge still waits for each generator to provide it with a value before comparing them, using the same comparison method as before. It keeps track of the order it receives values. The first value from each generator is compared, and then the second value from each generator, and then the third, and so on. And then he still does the same thing of comparing their bottom 16 bits. And so, you know, the idea is, hey, well, if they're not You know, if they don't end with 1, 0, 0, they're like not that likely to collide. So they try to find more matching values, and we certainly do get more matching values per judge attempt, but it means we have to generate many more trial numbers. So now we only do 5 million instead of 40 million values. Okay, so how to implement this? I had not extracted this judge function in part 1. It ended up, I thought that this might be something that would be taken out of in part 2, and I only used it in one place, so I just used it in line. But now, this is something we use for both part 1 and part 2, so it deserves its own function. Part 1 is basically unchanged, except that we are using the new judge function. Part 2, this is, again, an example of where I kept getting the numbers mixed up. This go function takes 3 integers as arguments, right? And one of those arguments is this one is the factor they multiply by, this one is the seed that they start with, and this one is the divisor that they check for before returning a value. And like, I must have messed these up at least 4 times, like just trying to debug why I was still getting the wrong answers. And if they had been in like some new type wrappers, it would have been much easier, I think. I could have gotten it right once, double checked, and then made it impossible to get it wrong again. Anyway, so this go function, of course, takes 3 arguments, but we're only actually defining it with 2, because we're going to compose it with this iterate, right? So we say iterate next of factor, starting with the seed, the implicit last argument, and filter the results to those that are equal to 0 modulo the remainder you are given. And like, that's sort of it. It's a really, really simple part 2, but because of like not having good type discipline, I spent, I don't know, at least half an hour on this, like trying to debug why I was getting the wrong values, and it was because like I had mixed up B with 48271 or something like that. So let's actually see what would happen if I were to define new type factor equals factor integer, new type seed equals seed integer. What happens if I do this? We take a factor and a seed. You know what? Forget the seed. Let's just add this one new type and see how much it helps. Factor of factor, f. Okay. So we're gonna, I'm turning on Intero here so it can tell me where the problems are. Okay, there's one. So first of all, it's saying, well, gosh, this is supposed to be a factor, but it's a number. What's the deal? Well, okay. Double check. First of all, is 16807 really a factor? Let me go reread the problem real quick. A uses a factor of 16807. Yes, I'm doing this correctly. Okay. How about this one? 48271. Yes, that's also a factor, so we can wrap it in a factor. And now it's highlighting these again. Factor. Factor. And we can destructure it here. Factor f, next f. We shouldn't destructure it here because next wants a factor, not just a bare integer. And so suppose that I mixed it up here. I did this. With my previous implementation, this would have compiled and type checked and run, but given me the wrong answer. In my new implementation, it says, hold on, you can't do this. That's not a legal thing to do. And warns me exactly, well, you're passing a factor where you expected a number, and you're passing a number where you expected a factor. What's the deal? So I think that's an improvement. As long as every time you write this factor new type, you check the specifications and say, wait a minute, is a factor really what I'm expected to use here? If it is, the type system is helping you. And if it's not, the type system is helping you even more by stopping you from accidentally using a factor where you meant to not do so, right? Anyway, so this is all pretty simple. Part 2 is boring. And it gets the right answer. Let's actually just double check that, of course. Day 15. And I think it runs pretty quickly, but not like instantly. Now, while this is running, I'm going to go check real quick what's in day 16. Is it something I can cover really fast, or do we need a new episode for that? Yeah, I guess we need a new episode. Okay. Fine. So it ran, and we got 592 and 320. Lovely. Are those still the right answers? Of course they are. 592 and 320. So, I don't know. The main lesson here is about, like, sometimes in Haskell, the type system gets in your way. Or it can feel that way anyway. I struggle sometimes with defining the type for a thing that I mean to do. And I think that that's mostly because I get the implementation wrong. I'm like, the type that Haskell infers makes no sense. And it's like, well, your type makes no sense. And I'm like, yeah, I mean, that's because my implementation was wrong. Thanks for letting me know. But I wish I understood the type system a little better to figure out what I meant to do. So anyway, sometimes it can feel like it gets in the way. Arguably, sometimes it actually gets in the way, but I'm not really enough of an expert to say. But it's there for you to make use of. And one way to do that is to define stricter types for things if you want to be explicit about what's happening. I've done that before with some type aliases. Like, I think in day 14 we had one, right? I had a type alias, 2 type aliases. And that's just for convenience for shorthand, and also for, like, being explicit about this isn't just a tuple, it's a coordinate. But the compiler sees those 2 types as identical. You can pass a tuple where a coordinate is expected and vice versa. The new type is more extreme, more rigorous. You have to actually, it introduces 2, what's the word I'm thinking of? 2 incompatible types. It makes factor a type that is incompatible with integer, whereas before a coordinate was compatible with this tuple. And in order to convert, you have to explicitly convert, which means it's easier to make sure you understand where the conversion points are between the code where this is labeled as a factor and where it's just treated as an integer. So anyway, that was day 15. Hope you guys have enjoyed. Thanks for watching, and I'll see you next time.